Okay, to wrap up video here, we'll start with this idea of a state function, something that doesn't depend on how you get there, as long as you get there. And one of the biggest ones, let me pull up this portion of the notes here. It's called the standard enthalpy of formation. So it's the heat change to make something. And the way it's defined, the change in the enthalpy, delta H, for formation has this little f, like if it was a combustion or a solution process, it would have a different little subscript there. The little degree looking symbol means under standard conditions, which we sort of line out here at the top of the page. So it is defined as the enthalpy change to form 1 mole of the substance from its elements in a standard state. And so an element then gets assigned a value of 0. So it's almost like we say, we have the elements as our Legos to play with. We know we can't measure the total enthalpy in them, but if we can get a change to go from them to something else, it's almost like we have an idea of the energy content of the something else. So let me show you some examples of some things that are processes that qualify as being heat of formation equations. If you take a mole of hydrogen gas and a half a mole of oxygen gas and react them and make a mole of liquid water, then the physical states are standard for all those elements. A gas for hydrogen, a gas for oxygen, and liquid for water. The delta H for that process is about negative 286 kilojoules per mole for water. So what we say is that that is the heat of formation for water. If you just were to say make methane or natural gas from its elements, solid carbon, which is the standard state of carbon, a couple of moles of H2 gas, makes 1 mole of methane. So that equation fits the definition. So that equation definitely has an enthalpy change. There's some energy change associated with it. But because it fits the definition, that process right there would define the heat of formation for methane, which is also exothermic, negative 74.9 kilojoules per mole. So enthalpy and entropy, and by extension, because Gibbs energy comes from those, they're all state functions. And so that's why we can do a calculation like I did in the previous video and like I'm going to sum up here, that if you do the total amount of that quantity for the products minus the reactants you started with, you can get the change of that. There's also a law we'll have to deal with called Hess's law that basically says that the enthalpy of a process doesn't depend on how you get there. For example, if I eat sugar and digest it in my body, there are many, many steps it must go through. If I just burn it on the stove, I also can get energy out if I measure what comes out as it burns. It doesn't matter how I do it, sugar is going to give up the same amount of energy. And this is because enthalpy is a state function. So this allows us to find the delta H for a reaction by taking these heat of formation data, using this whole, take all the enthalpy of formation of your products minus the sum of all your enthalpies of formation for your reactants, and that same thing that I showed on the previous calculation, which I'll show again here, actually works because of the idea of Hess's law, that enthalpy as a state function can be treated like a state function. Let me show you an example here on page 355 of your book. There is a table there that's heat of formation data. And so it's got in it a heat of formation for methane. And well, it doesn't have one for oxygen because it's an element, it's 0. It also, though, has them for carbon dioxide and water. So methane, CH4, plus 2 O2 gas makes carbon dioxide and a couple moles of water vapor. The question is, what's delta H for this reaction? What's the enthalpy change for doing this? We might expect this to be exothermic and have a negative value because this is burning natural gas. You would think it ought to. So what I've done is this whole products minus reactants thing. The products include 2 moles, and if you check, this negative 241.8 kilojoules per mole is for water vapor from that table on page 355. There's also a mole of carbon dioxide gas. So 1 mole of that at negative 393.5, notice it's kilojoules per mole, so I have to take into account how many moles I have on these. But that would be the sum, if I added that up, of all of the products. Now the reactants, there's only 1 mole of methane involved, and it's a negative 74.9. We just showed you that value. but it's also in the table there, plus 0. The reason it's 0 is because every element has a heat of formation when it's in a standard state, like O2 gas, of 0. So if we were to look at how this math comes out, I'm not sure why that's stuck in there. Negative 877.1 kilojoules is what all of this adds up to. That's for the carbon dioxide and the 2 moles of water. Minus, we got to take a difference between the products and the reactants. Now the reactants only have this one value, and so it becomes a negative minus a negative, so that's like adds a positive to this, and we're not as negative as we were, but we still have a negative 802.2 kilojoules, which makes sense because that ought to be giving off some energy when it happens. There's another example of this. You can look at the bottom of 356. And there's another interesting little thing at the top of 356 that's a Hess's law kind of thing. I'm not going to like work all of those right now. This is something that I would invite you though to look at and ask questions about. And so I want to kind of bring this to a bit of a conclusion in this last video, if I can. First of all, why on earth do I have all of this mess written out? And if you'll notice here, let me kind of extend my page if I can so I can bring this all on here. I wrote one where the delta G, the free energy change for reaction, is the sum of all the free energies of formation. That is a table I haven't talked about, but if there are enthalpy tables and if there are entropy tables, you figure since delta G comes from them, there might be free energy change tables, and there are. So the point, okay, it gave me a note my microphone quit, so I don't know if it really did, but anyway, free energy change for reaction, if you know all of the standard free energy changes to get whatever the product chemicals are, and you subtract that for all the free energy changes for the reactants, that's the only one I haven't done for you yet. I did one with enthalpy, basically doing the same thing right here. My first example back on the other video was taking all the standard entropies of my products and all the standard entropies of my reactants and doing a subtraction on them to get the change of entropy for a process. But I guess the point I'm trying to make here on this thing is that because all three of these things are state functions, that products minus reactants thing works for them all. So you can actually calculate the free energy change or the enthalpy change or the entropy change for a lot of processes by having these tables. So what if a delta G for a reaction comes up negative? Well, that means that thing can be spontaneous. If it comes up plus, it's not going. No way. It cannot happen. Delta G is the only one that's a guaranteed predictor of that. Now, if we look at the enthalpy change, the heat flow, delta H of a reaction, if you could take the heats of formation of all your products, since that's them being made from the elements, it's almost like their enthalpy content, although it isn't truly, but we can kind of treat it like it is, because we decided to make elements 0, and so anything that's not 0, we can kind of go from there. But if you take all the free energy, all of the enthalpy of formation for all your products, all the enthalpy of formation of all your reactants, add them up and take a difference between those, because these are all state functions, that ought to give you delta H for a reaction. When you get a delta H for a reaction, it does not prove if it can happen or not. But if it comes up positive, that means that this is not really favored by the natural way of things according to laws of thermodynamics. If it comes up negative, where energy is being reduced in the system and given off to its surroundings, then actually this is more likely to occur. Again, the very first one of these I did for you where you could do products minus reactants was entropy. Be careful, because the units of entropy, like joules per Kelvin, are different than heat of formation, usually like kilojoules per mole. So if you're going to use these two things together, like let's say you get a delta H and a delta S, and you're like, well, I'm going to find delta G from them because I know delta G is equal to delta H minus T delta S. Just make sure you pay attention to the units because they typically are different. But if you take all your standard entropies of your products, taking into account how many moles of each there are and everything, and the same for your reactants, and take that difference, you can get the overall change that it would take to go from reactants to products. And if you get a number for that, it tells you something about that process. If it's a positive number, then that means that that is an increase of entropy, which is an increase of disorder, which means the second law says that randomness is going to increase in the universe one way or another, and this would be a favored thing to occur. If you get a negative number for that, that would be the system getting more organized. Once again, I'm not saying that we can't input energy and have a process there where we can maybe get an entropy change where things are getting more ordered. In other words, a negative number for entropy. But it is not normal, nor is it favored to occur spontaneously in the universe. So there's a lot here. This is all a lot to take in. If you don't read the book and go through and ask questions and work the example problems and think about what you're doing, you'll have a lot of trouble really getting these concepts down unless you spend a little time with them. Hopefully with the videos we have, you can, if you need to, watch them more than once to try to make sure it's all starting to mesh. But this is what drives everything. What we've done is we've found ways to predict what will happen and what won't. The only number on this particular page here that definitely will predict a reaction spontaneity is delta G. Give it a negative number for the free energy change in the system, it will spontaneously happen. If it's a plus, there's no way that will spontaneously happen. These other two can be calculated in a similar manner with this products minus reactants thing, if you have tables, but they are not necessarily guaranteed. They are just predictors. They may be favored or they may be not. If both of them are favored, like a negative delta H and a positive delta S, then yes, that one's going for sure. But if it's fighting each other, like some examples often do, then it's going to depend on what the temperature is, whether or not it can go. So the other major equation, I'll just take a second to write. Don't forget that even though you can do this products minus reactants things to find a delta G or a delta H or a delta S, the equation that relates all these changes to each other is that change in the free energy is equal to the change in the enthalpy minus the temperature times the change in the entropy. And if the delta H is less than the T multiplied by delta S, and that sounds like a poem. In fact, it might be a song. We'll see. But if that number, if the energy required is less than what you can have dealing with right here, then the process can happen spontaneously. And I say that because if that is true, if the delta H number is smaller than this term here, you are going to get a negative number for that delta G, and that proves it's going to be spontaneous. So anyway, that is sort of a complete overview of thermodynamics, as much as you probably see in a high school course, and I hope that these videos will be helpful. This will hopefully be the last one in this particular series, I think.